our past rather career, me and Menachem has started very similarly. We have been in the army doing MSc thesis, and it has been my pleasure and honor to work with him for many years. Not so recently when he was president, but still. In fact, I think it started to diverge when he decided for some reason that as a volunteer for many things, if he will begin, then instead of volunteering to many small things, he will volunteer to one big thing and will have more free time. I have some doubts about this argument, but it has certainly led him to be president, so you don't have to do politics. And in fact, the time I have most free time to speak with him when we were both at Madras in native in some conferences. But still, several of my best work have been with him, and I have certainly benefited much from discussions with him and criticism. And I will speak on a topic which connects to one of our work, which is dear to my heart. I hope to him too, but who knows? Okay. So, the paper is in Journal of AMS. I forget. Okay. It says that the question was bound. There is a lambda-free Abelian group not free of cardinality lambda. Okay? Now, you don't need here to, the audience here probably is not so much into algebra, but still I hope Abelian group is known, and what is a free Abelian group is just direct sum of copies of Z, yes. Now, this is equivalent to lambda. There is a family of countable set. P has no transversal. This is a one-to-one choice function, but every subfamily of smaller cardinality, okay, P is lambda, has. And there is much more to be said on this, but okay, and the surprising answer we can, it is unbounded below first fixed point. The first fixed point is aleph 0 plus aleph 0, aleph 0 plus, okay? So it is the first aleph which is the same as its index. This was quite surprising. Usually you assume the bound will be much smaller. There have been much history before this, but unlike some people here, I don't lecture only on mainly on the history of mathematics, so I will not deal with it. Now, there are many things, questions which this open. For example, one of them is, what exactly is a set of cardinals for which we can get we can get here. Is it only the one which proven explicitly there, or there are more? In fact, I'm exactly now dealing with it and hopefully building more, but this is not the, well, I lecture on what is at least written and typed and not what I just start to write. So there are one other direction is there are many constructions of abelian groups and modules which are, we like them to be free and have some extra properties. Much work on a ring, which ring R can be represented as the endomorphism ring of G lambda free abelian group. This is, okay, there is a book of Gebel and Trelfage. I'm quite sure I don't pronounce it well, but probably there is nobody here to correct me. What? Trilify. As I spell it at least correctly?
There's an I after the R.
Oh, okay. Well, so you have just proven me correct. I have said that I'm probably wrong, and you have just proved it. Confirm my conjecture, yes. Okay. So there is, and there are many such representations and such. And easiest thing is G is not Whitehead, or what is very close on G Z is 0. Okay? So this is a miniature version of it. It just makes the what? This is home. White, I don't say that this is equivalent. The equivalent say it is X. However, X is a little more complicated to define, and home is easier, and in fact, the two things are closely related, yes? If you think about it, if you have, it says a Whitehead, it says that a derived group, something is a direct sum and a copies of Z, and this lead a homomorphism, so never mind. But I don't want, there are algebraic aspects to the work, but they are not the one I stress here. So now there were many works of the following two kinds. One, assume V equal L lambda not weakly compact or consequences, that is, there is a stationary set which doesn't reflect on cofinality Aleph 0, and you have diamond, or just diamond S, S, stationary, not reflecting. So here you get the maximum what you want, yes? But, well, but like many good things in life, there is a price, yes? So the price is that you assume, you don't prove it in ZFC, but
What do you mean the maximum? You say the maximum.
Yes, okay, in this, it is a maximal amount of freedom, yes? So you get lambda free of cardinality lambda, say, representing some suitable ring. I didn't say the ring has to satisfy some conditions. So I don't look at exactly them. I will rather look at this. So there is a group like this, which is lambda free of cardinality lambda. And you get it for every cardinal which is not weakly compact when in regular. Okay, so this is maximal you can hope for, yes? So you get everything, but you have to pay a high price. Well, this is very reasonable. To build in ZFC, e.g. in lambda is mu plus mu is mu to the aleph 0, G is aleph 1 free. Okay? Use backlog box. I will say so. So in this case, you get very reasonable, but the amount of freedom is meager, yes?
What is PB
Black box, yeah. You use a black box principle, which is it is provable in ZFC, yes, that it exists, and it is some guessing. I started in model theory in number of non-isomorphic models, but then I find that it is useful in Abelian groups and in many results like this. Okay, so can we get better than aleph 1 in ZFC? Yes, this is a question, yes? So,
you mean aleph 1 free, non-free?
yeah, well, okay. It can't be, if it represents some a priori ring, it is not free, or, you know, forget. It has no homomorphism to that, then it isn't free, because if it is free, it is a direct sum, and we have 2 to the cardinality. Yeah? Let's see, i.e., can we get aleph 2 free or lambda free G G Z is 0, yes? So this takes the simplest algebraic case, which is complicated enough, and I think it is a good test. And we want to increase this. What? Aleph 2. Aleph 2, well, first, or lambda, yes? Or till when, for which lambda, yes? So, of course, from now, I have once a short argument with Yoram Linienstrauss. I have told him, oh, I have to say something interesting in small Banach spaces of cardinality bet omega, or aleph omega. He looked at me and say, oh, this is very large. Okay, so of course, this is not an argument which you can prove correct or incorrect. But I think that at least probably for most set theories, the first fixed point look quite small. Certainly, it exists in ZFC, so by definition, it is not large. Still, there are quite many cardinals up to this first fixed point, and we want to know where the truth is. Yes? Can we build such things? Can we not build even for aleph 2? Or can we build in up to the first fixed point? Or there is something in between? Okay. So Yes, yes, yes.
So can you get a counterexample? Let's say a group that maybe not alpha 2 free, but that on GZ is 0, but every small subgroup has got many homomorphisms into Z. Without
No,
being
okay,
free.
this is, okay, what you say is a different question. That is, instead of asking for which, this you can ask forget about freeness of the Boolean algebra. We redefine free as having many homomorphisms. Exactly. But this is not what
Let's say I know it's a non-standard thing.
Yeah.
Free star means that every non-zero element, this is my own private
Yes,
definition,
yes.
but free star, that every non-zero element there is an homomorphism into Z which stands for something different than zero.
This is essentially separable, because if the element is mapped to 1, yes, this means that it is a direct summand. If not, it is and this I think is called separable. And now you can go to more complicated things. What you say, I think, also have a name, but is somewhat more complicated. And you can certainly ask about this, but somehow the question, I think people were interested. Anyhow, this is this version, which I think is reasonable. So I don't know. I will give you an answer in the end, okay? If you stress on it, I will tell you now. But I think the story would be nicer if I say this. So, of course, there are two parts to it. Or depend what is the answer. If the answer is aleph 2 or the first fixed point, we should have one proof. If it is in the middle, we should have two proof, combinatorial building and consistency. So, but let us see, relevant for the aleph ends. Yes. We look at, e.g., consider x belong to k 2 to the omega. Okay. Call this lambda. Eta restricted to m I is eta L prime L less than k. Eta prime L is eta L if L is not M, and is eta L restricted to I if L is equal to M. So, whereas usually in those proofs we look at a family of omega sequence, we look, there are relevant things, say also in the work with Menachem and earlier, etc. But usually the point is that we have induction, and so we do not need directly so much to deal with it also in compactness. Never mind, look at this, and look at the family. Let A eta is M less than K, I less than omega. Now, surprisingly, theorem A is aleph k free. I don't remember if it is also aleph k plus 1, but never mind. It is aleph k free, and if continuum bigger than aleph k not free. Okay?
How do you define the direction?
No. I have here say it is I to use the transversal version. Aleph 1 free transversal version. Or if you want group, you have group. The group is sigma x ni adding sigma you add such infinite sums which translate it. But I think that the transversal is more, at least in this audience, more clear. I think also absolutely, but okay. Say again? Say again?
You can translate freeness into transversals, but how about Whitehead being a Whitehead group? I think you cannot translate.
Okay, and now you can also answer the Whitehead. The point is, the freeness is, as I have said here, suppose the continuum is large, it is aleph k free. However, if the continuum, then you have a black box which help you prove that it is not like if you look at the, say, my first work on Whitehead problem, I used diamond to this. So here instead we use black box. Okay? So you have to do some work. It is not given to you for free, yes. But still it is. Yeah.
When you use your standard way of turning a counterexample for freeness for transversal into the group example.
Yes.
Is that group satisfied at all GZ0?
No, but as I say, you can correct it so that it wouldn't be. It is not that as it is here, it will here GZ is not 0, but correcting for each infinite sum using black box, we can. Okay? Okay, so now then similarly, then I have works with, this can be even if continuum small, we can replace 2 by, I don't know, by bet k plus 1 and build. Yes? Yeah. And build. Okay. No, I'm sorry, this was not, but here, if anyhow, in the FC, that is, we look at sequences not of 0 ones, but of some bigger ordinal, we can build such thing. What I say there was inflamed. So yes, for Aleph n. So Aleph 2 is not the right bound. Yes. And then some work with Gebel, Herden, Strugman, support the thesis that those constructions are good for other similar, more complicated problems. But, well, what about Aleph omega? I have tried to this, and I have a very frustrating work in the sense that I prove it except for some except if set theory is very peculiar. It satisfies things which are close to GCH on the one hand, but it cannot satisfy it too strongly on the other hand, etc. Almost. Most set theories. Yes, you know, if you look at a problem and you can't prove anything, it is not frustrating. Just you don't know anything. If you almost, you know, and you see everything is, but it doesn't converge, and it looks like epsilon is needed, but it doesn't. So, okay. So now we come to the solution. So I think there is some famous book which say what is the answer? Okay, so the answer is Aleph omega 1 times omega. The answer is how much you can prove in ZFC that there is a lambda free and not free. Okay, assuming what?
In the strongest sense of home?
Yes,
Okay.
yes. I.e., can we, there is lambda free G on G. ZFC proven is 0 if lambda less than Aleph omega 1 omega. Okay?
All cardinals?
I don't understand. No, I didn't say exactly lambda free, but I say, well, there are such construction up to this and not later. But as we'll see, the ZFC part, the CFC part not work for all rings. For all rings, we probably, I'm not sure, we need molecular. But for this problem, for usual problem, this is right.
Are there in ZFC construction? Namely, in ZFC you can construct for all the cardinals up to...
Yes. Well, depend. Half of it is ZFC. The other half is super compact. So, infinitely many super.
You cannot
Yes. Let us see. The fact that it is a lower bound is a ZFC construction.
including the singulars. You don't get...
No, I didn't say exactly so. It just means that it is unbounded. Remember that previously we have said that we want lambda free of cardinality lambda. So this we totally waive, is irrelevant, yes? We usually have it like here. We want Aleph k free, not free, but of cardinality bet k, or bet k plus 1, I don't remember, yes? So previously everything was in exact cardinality. But now it can be far apart. You can ask if it is lambda free, not lambda plus free. Okay, I didn't look exactly, but no, in fact, you know, if we want to prove in ZFC, we can't prove it, for example, for Aleph omega squared. Yes? We know in our works this is proved. So you can't hope to prove it for all cardinals. But this means arbitrary. In fact, the construction is for. Okay? So.
In this particular, can you get all the cardinals up to Aleph omega?
No, because by my work with Menachem, for Aleph omega square plus 1, if something is Aleph omega square free, then it is Aleph omega square plus 2 free.
But I mean up to Aleph omega.
No, for the Aleph n, I've known it earlier. But the question was, maybe it was reasonable to assume that if it is Aleph omega free, then it is free. But so if it is Aleph omega free, then there are non-trivial homomorphisms. Yes, so this was, in some sense, where I was stuck. And this tells that not only we can go higher than I didn't know to have Aleph omega plus omega, yes? Okay, you know, giving up to Aleph omega square. So not only this, but in fact it is Aleph omega 1. But for the Aleph omega 1, we need also some this. We need a different group theory, which is not, for the problem I state, is fine, but if you want every ring, then things become more complicated, but I didn't yet sort it out. Okay, so now, as I have said, there are, I have, I'm sorry, I have no idea how much time I have left, so maybe it is your role. So, and secondly, what? 15. So probably I will be able to, well, what you want to hear first, the consistency or the ZFC part? Okay. Yes, like many, what? Both. Okay, so tell me when to stop, okay? No, when to change gear. No, I mean when to change gear. Okay, so, what?
The birthday boy has to decide. The birthday boy has to decide.
Yeah. Okay, what you want me to start with? Okay, so I will start with the forcing. In our paper, we have kappa n super compact and preparation and labor and more. Now, and let kappa minus 1 will be Aleph 0, okay? And maybe things close to GCH, and there are somewhere no bad stationary set in relevant places, never mind. So, or maybe, kappa minus 1 is Aleph 0, less than kappa 1. And the forcing, okay, maybe we first say what was the forcing in my paper with you, in our paper. So in our paper, the forcing, there are many parts, but the main thing is that for between kappa n and kappa n plus 1, well, including 0, we choose a subset, a set of cardinals. We assume GCH. We shoot a set of cardinals in the middle, which is nice in the sense that its cardinality is smaller than the first element. Yes. Bn regular cardinal kappa n plus 1, and we use Levy collapses such that the set of cardinals, okay, product of Levy collapses, not collapse, is essentially closure B plus limits plus successor of singular. Okay, so we collapse them, and Bn is less than minimum Bn, or something like this, okay? So this will make, or in fact maybe better is, what? So really, kappa n. Yes. So the kappa n will be, this is the way to make it the first fixed point, because we have to make between kappa n and kappa n plus 1 that there will be no fixed point. In fact, it should be smaller. So such product of Levy collapses is what we do. And then if we have, of course, their normal ultrafilters for the supercompactness, we will guess a name and blah, 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 eventually have some reflection principle, okay? Now, we change Bn has order type omega or omega 1. Yes. Now, okay, this does not give the result because we have here GCH and it is works. This is, but this is change 1. After forcing, this is Q, we force Martin axiom plus continuum is sigma kappa n plus, okay? Now, the point is that if we have Martin axiom, then, okay, in fact, when I work on with Martin axiom on those, I check exactly which are the groups which are not weighted. And they characterize, there is a reason for their not being weighted. Now, in most expository works, people stress the easier case of Aleph 1 free. So Aleph, or strongly Aleph 1 free. But in fact, we need here, well, not the exact characterization, but saying that if you have Martin axiom and you have a group, Abelian group of cardinality less than the continuum, and it is not weighted, the reason is that some derived forcing fails the chain condition. And by definition of failing the chain condition mean that you have Aleph 1 elements witnessing it, yes? So if you look carefully, you have a subgroup of cardinality Aleph 1. So this is central here. If G not weighted, G less than continuum, then G has cardinality, has subgroup it is not weighted, so it can't be free.
G is a subgroup, a non-free subgroup.
A subgroup, yes, a non-free, yes, has, well, a free subgroup of cardinality Aleph 1, or, okay, at most Aleph 1, but otherwise this is not. Now, however, we have, now, but we have to analyze this. This is by itself is not enough. We have to analyze this. Say it again.
Sorry, before this, once dual collapses.
I don't know.
Dual collapses, you have this says BN. Do you choose them
Generically? Oh, they are part of the generic choice, yes? They are not, you don't decide them a priori. You force them, they are names.
And how to ensure that you will have unbounded many of such Aleph 1, also generic?
No, this, okay, so, okay, I don't have, yeah. But this is not very.
Essentially, we imagine the case that you do the collapse above the supercompactness. then you pick the thing which reflect them with respect to the normal order filters that will exist after you do the collapse. Okay.
It is. I try to say what is the difference. Yes, I didn't. You know, if I want to lecture on what similarity, I will have more than an hour to explain the paper with Menachem. Yes. No, there is, but the point is what we should change. Yes. Also, there you start with having many inaccessibles. Yes. You allow above the first fixed point not only to have certainly many fixed points because you reflect what is upstairs, but you want to allow inaccessible. But even if just you have third order fixed point, you have to do something to collapse. Yes. Okay. Now, however, I can't say it here. We have to use analysis of free context and the proof, or build on the proof why freeness for transversal is equal to freeness spectrum, freeness spectrum for Abelian group. So we have to look carefully at them and then see that because of the quotient I have, that you have a problem of size aleph 1, things can be close together. So I'm sure this is not satisfactory, but I suspect that this is it, what I can say here. Now, we are we are saying what is the ZFC. Okay, the ZFC we use, okay, how much time I have left? 2 minutes. Oh, 2 minutes, okay, well, we analyze mu, which is a bet omega 1 times n. Yes. So without loss of generality, 2 to the mu is mu plus. This is not, otherwise we get a much more free things. And so we can find okay, if f delta is pi, where lambda and I regular, increasing with I, and as free as we can. Now, it is not really free, but the difference is we don't correct it to C delta belong to some S. Okay, in mu plus sub C delta is delta, order type C delta is omega 1. Now, but we do not ask for free directly, but for theta 1 less than theta 2, C is theta 2, theta 1 free, which means if U belong to S as cardinality less than S2, then we can divide it to UI, I less than. Each U epsilon less than theta 1 and each eta belong to U epsilon is free over union of the previous thing, okay? Now, so we have many pairs for which it is free, and we have many pairs for which it is not free. However, if we look at a product if we do it for several CL, L less than K, K large enough, in the product we get the desired freeness. I think help for the spectrum for Abelian. Yes. That is for which to have more cardinals where we have lambda free, not free, exactly for not. But this I didn't yet write, so but the point is that though we get for each construction by PCF a structure, we get only freeness of this. We get the freeness only for, except few exceptions. The number of exceptions is usually, if we look at here plus n and we look at the cardinals below aleph omega 1 n, then for each aleph omega 1 k there will be few problematic cardinals. But as long as we are below aleph omega 1 times omega, for some aleph omega times n fix n, then we will have a priori bound number of those. And if we take product which is of more, then we regain the full freeness of them. And of course, then we have to prove that there are black boxes, and the free Boolean algebra have to construct building something over aleph 1 and not over omega sequence, but over some omega 1 sequence. Really, the filter, like product of boundedly many below aleph 1 times boundedly many below omega. So this is what we have to do. Okay, thank you.
One short comment. The question I asked in the middle was foolish. I asked the question about whether fourth cardinals you have freeness for essentially what I call free star.
Yes.
That's actually the paper with Johan. We have a complete answer, which actually it's essentially equivalent to some kind of strong compactness of the cardinal. We call it omega 1's strong compactness.
I see. Okay.
And it's a large cardinal. So anyway. Okay, so that was a foolish question. We know the answer. Just my question now is, in our paper, when we get compactness at aleph omega square,
yeah.
you can modify it, you know that very well. You can modify to any countable interval of cardinals.
To any?
Countable interval of cardinals above alpha omega squared. We have compacted
Yes.
the seven alpha omega squared up to alpha plus 1 for every countable alpha. We know that alpha omega 1 plus 1, there is no compacted.
Okay, but
So you get it on the interval. This looks like
I have stated I have thought in the last 2 days on, but not particularly on this, but on the more on aleph of aleph omega squared plus 1 as successor. I in fact I didn't think about it because I didn't remember if it was resolved or not and haven't yet checked it. So before I check
as far as I know, it's not resolved.
What?
As far as I know, it's not resolved. We don't know
Yes,
if
yes.
we get the whole interval between alpha omega squared and alpha omega 1.
No,
to
it
be
is.
compact, yeah.
I will check it, but I can't.
I have a very simple question. I cannot believe, but you forgot to give us the code word for this paper. Is there a number?
Oh. This is PCF almost. Okay, so
So the
Is
one
this
you're
clear?
working on now is 1028, the one that you
Yes.
spoke about today.
yeah. This is as a context of this.
So in a couple of years, we look it up and we see all the details.
Yes. No. Now is at where because it is not updated. I am here marking it, so I didn't choose a correct, but okay, probably this month it will be